So what we're going to be looking at today inside of this video is explicit formulas for geometric series. So a geometric series, or a summation of a geometric sequence, is one of the form we're going to have the sum k equals 0 up to n minus 1 of a times r to the k. Couple things to get here, that a is your initial value, the initial value inside of the sequence. And r is the common ratio. So what we're looking at is we're basically taking a summation of a geometric sequence. Now, the explicit formula that we're going to end up getting here is going to end up equaling a times r to the n minus 1 over r minus 1. And we'll talk for just a second about where did we get that from? Like, where does that come from? So a couple of things. We'll take a look first. We'll break down the sum k equals 0 to n minus 1 of a times r to the k. And the first thing I'm going to do is notice that that's a scalar. And so I can pull the scalar out. And so I get a times the sum k equals 0 to n minus 1 of r to the k. So now what I want to do is I want to actually examine this summation right here. So the sum k equals 0 up to n minus 1, if I were to write it out of r to the k, is going to end up equaling, we'll have it be r to the 0 plus r to the 1 plus r squared plus, and we're going to keep going until we get to r to the n minus 2 plus r to the n minus 1. Now if I go in here and I actually multiply this sequence here, or excuse me, that summation here by r minus 1, let's see what happens when that happens. Okay, so we're going to take this, and so I'm just going to forget this for just a second. We're going to leave it over by the side. We're going to go multiply it through by r minus 1. So we first out, this is a 1, right? So this is going to end up equaling r, and then we'll get r minus 1. So that's what happens when I take r minus 1 and I multiply by r to the 0. And then plus, and we're going to get r times r, so that's going to be r squared minus r. That's what happens when I take r minus 1 and I multiply it by r. And then when I multiply r minus 1 and I multiply by r squared, I'm going to add plus, come over here, plus r cubed minus r squared. And then I'm going to keep doing that, so I'm going to add r to the 4th minus r cubed. And I'm going to keep going until I finally get down here to the r to the n minus 1. My last term is going to be r to the n minus 1 times r. So it's going to be r to the n minus r to the n minus 1. Okay? And if I look, I actually have a pattern here. And sometimes this is what we do in math. We look at these patterns. And I'm going to look at what I see here is I got a plus r, and I got a minus r. And I got a plus r squared, and I got a minus r squared. And I got a plus r cubed, and I have a minus r cubed. And I'm going to do that all the way down until I finally get rid of everything except for this plus r to the n, because there's no minus r to the n, there's nothing added on the end, and this minus 1. So this is going to end up equaling r to the n minus 1, and that's what we've got left over. So what that means for us, notice that we took this summation and we multiplied by r minus 1. So r to the n minus 1 if I divide it by r minus 1, it's going to actually equal the sum k equals 0 up to n minus 1 of r to the k. So my explicit form here, my formula, the sum k equals 0 up to n minus 1 of a times r to the k is going to end up equaling a times r to the n minus 1 over r minus 1. That's kind of neat. I actually think that's kind of cool. Let's now take a look at some examples. So we've got the sum k equals 0 up to 100 of 6 times 3 to the k. So the first thing I want to do is note that a, my first term in the sequence, is going to be this 6. Then my r is equal to 3. And n minus 1 is equal to 100. So that means that n equals 101. We just add 1 to both sides. So my summation then is going to end up equaling 6 times 3 to the 101 minus 1 over 3 minus 1, or over 2. We plug that into our calculator, and what I get is I get a really big number. I'm going to get 4.6383976 times 10 to the 48th power. Woo, that's large. But that makes sense considering that I am eventually going to be taking 3 to the 101st power. And so consequently, you're going to get a pretty big number there. All right, let's take another shot at this. Let's say, for example, I had the sum k equals 0 up to 100. And I have 18 times 2 to the k. Well, now I've got a equals 18. I've got r equals 2. And I have n minus 1, again, is equal to 100. I probably should have chosen a different one. Let's choose a different number. Let's choose 200. There you go. Doesn't matter, but there you are. So now n would equal 201. So my explicit formula is going to end up being 18 times 2 to the 201 minus 1 over 2 minus 1. Plug that into our calculator, and what we get a really, really large number as well. We're going to get 2.892488 times 10 to the 61st power. Woo, big numbers, okay? All right, so that's basically how you're going to use this particular explicit formula. So now let's go in and see what happens if we don't start out at k equals 0. So basically what we're going to do here is we're going to do a change of variable, and I'm going to start out at k equals 6. If we don't start out at k equals 0, we're going to actually have to do the change of variable so that we can use the explicit form. The explicit form assumes that you're starting out at your index at 0. Now, does it matter it's a k? It doesn't. It doesn't matter at all. But what we're going to have to do is we're going to have to actually do a change of variable. So what I'm going to do is I'm going to let j plus 6 equal k. The reason why I'm going to do this is because what I want to do here is I'm going to substitute j plus 6, and that'll equal 6 for k, so then j is going to end up equaling 0. Okay, and that's why I'm going to utilize j plus 6. So the bottom is going to go to j equals 0. The top, that's a k up there, so I'm going to have j plus 6 equals 50 for my top, so j is going to equal 44 when I subtract 6 from both sides. Then I'm going to go in here and I'm going to substitute in j plus 6 in for k. So this is going to change my summation. The summation of j equals 0 up to 44, and this will be 8 times 3 to the j plus 2. Or excuse me, 3 to the j plus 6, pardon me. Now notice that this is no longer a k, so we have a little bit of a problem, but it's not that big of an issue because all we've got to do now is use some of our rules of exponents. So this is going to be j equals 0 up to 44, and now it's going to be 8 times, and what we can do is we can separate these out into 3 to the 6 times 3 to the j. So this now becomes our a. So a now is equal to 8 times 3 to the 6, and r, again, is still going to equal 3, and then we'll have n minus 1 equal 44, so n has to equal 45. When we plug that into our explicit formula, what we end up getting is 8 times 3 to the 6th times, and this is going to be 3 to the 45th power, minus 1 all over 3 minus 1. Let's go ahead and plug that into our calculator. When I plug that into my calculator, what I end up getting is I get 8.614 times 10 to the 24th. So pretty large number there too. Notice what we want to do here is if we're going to use this explicit formula that we have to make sure that our index starts at 0. So what we'll do is we'll just use a change of variable in order to actually start our index out at 0. And then that way it changes what a is, our initial term, but that kind of makes some sense, right? That you change your initial term. But it doesn't actually change what r is, what our common ratio is, which also should make some sense too if you think about it a little as well. All right, so that kind of ends our lecture here. What you'll see now, you'll see that we've got, anytime we have a geometric sequence, that is that we've got some number times a common ratio to the kth power, as long as we start at k equals 0, and we'll head up to n minus 1, we get a times r to the n minus 1 over r minus 1, and that's our explicit formula.